Yeah, is math an art or is it a science? Like, what is your take on that?
Yeah, math as a science or an art. I mean, with all of these questions, whenever you talk about a big thing like mathematics and is it this or is it that,
Hmm.
I think those are good questions, but they're good starters. I think some people
Hmm.
treat it as like has to be this category or this
Yeah,
category,
yeah.
where really the question is how is it like an art and how is it like
Hmm.
a science, or how does it relate to art and how does it relate to science? But if we're putting, a line in the sand, I would actually probably go art before science
Same,
because
same here.
because I think science, what you fundamentally need in a science is to be observing something in the physical world.
Yeah,
And that's something that, math is certainly related, and math is the tool that we best use to describe those observations in the physical world. That's how math
yeah.
is with science. But it
Hmm.
doesn't exactly need that.
Hmm.
Um, whereas, like especially pure mathematicians, they just love things that look beautiful.
Hmm.
That's interesting.
Hmm.
I'm actually some of the stuff you were just talking about. I'm gonna try to find a talk that I watched recently that was talking about how AI might change how mathematics is done.
Oh, very
It was
much.
by Akshay Venkatesh.
Okay, cool.
Venkatesh.
Cool. Are you typing
AI.
it in the chat or
I'm trying to look
in
it up.
Zoom or?
Yeah,
Oh,
here
okay,
it
yeah,
is.
wherever. Okay, that sounds
It,
great. Yeah.
yeah, I'm gonna link that in the chat because I think that's a good one to watch. And it talked about with most intellectual technologies, one of the big things is like what happens when one task becomes 100 or 1,000 times easier,
Yeah,
and
yeah.
how does everything kind of rebalance itself? Like we use calculators and we do use computers. You mentioned the four color map theorem
Uh-huh.
to like just sort of bash out a lot of stuff. Like for a little bit, I took this class by this computational number theorist, and the way you would
Oh.
prove a theorem is you would prove it for like say every elliptic curve of like say rank less than bigger than some amount or with coefficients bigger than some
Hmm.
amount, and then you just check every single elliptic curve under that.
Yeah.
You just have
Hmm.
the computer
Hmm.
just check all the other cases. And
Right.
what Akshay was talking about is that not so much what LLMs would do. This is something that we've had a little
Hmm.
bit for a little while now. Is that most of what we do in mathematics is we make these little logic games. Like
Yeah.
maybe in linear algebra, we're playing with like vectors, matrices, whatever, and we
Hmm.
can play these logic games and get results. And what might happen is we might still make these little logic games, but in the future we'll just always be working with a computer, and then you press a button on the computer and then it plays the kind of games. It
Yeah.
does the little algebra steps and it tries to spit out some results. And
Yeah.
so
Yeah.
and there is a good question of like what do you value in terms of understanding? Because in some ways you might say like, well, I want to understand that part. I don't want to just black box all
Yeah.
of the things
Interesting.
there.
Hmm.
And
Hmm.
one example that he gave is that there are these theorems in the about Lie groups.
Okay. Hmm.
And you can prove a lot of them in general, but there's
Hmm.
actually only so many families of Lie groups, and you can prove them like case by case for each family. But the way you prove it like case by case is a little more, I don't know, idiosyncratic, and you might think it's like, well, you want the general proof because that's kind of more aesthetically pleasing. And so it will be
Right.
interesting
Right.
because I do think the future is that you will be doing mathematics with these machines, and it's a
Hmm.
question of like, when are you done? Are you done when you can prove the theorem, or when you have the
Hmm.
proof of a certain form? And so I think
Yeah. Or both.
big changes
I
are
mean,
coming.
yeah, yeah. I felt for a while that there could be some kind of new field of work that's like math engineering. That's
Mm,
like really about finding new results, like new truths in math, and maybe that is kind of like the people who are asking the right questions to the super LLM that's great at lean or whatever, and the computer, the system says like, yes, this thing is true, and there's some, you know, very difficult argument that we can't understand immediately, and
yeah,
then the math, like as math as an art type of people that we've been for a while, then we go try to find a human understandable version of the reasoning for that. Like,
mhm,
is there a way that we can, make a classical proof of this result, and then sometimes
mm,
the classical proof, gives light to new questions like that the
Hmm.
math engineers are asking and like working toward. So I don't
Yeah,
know. I feel a lot of software engineers might go into something that feels more like that, and to a way lesser degree, that's like
mhm.
formalization of everyday software systems with something like lean. Like I would love to
Mhm.
prove that my self-driving car is not going to you know do whatever it shouldn't do.
Yeah,
Things like
well, I
that.
have a friend in like computer security, and oftentimes they run SMT solvers
Yeah,
where
yeah. Hmm.
you just want to prove that, say, you can't have a code injection if the input's smaller than some amount.
Yeah.
Um,
Hmm.
and so it's definitely formal methods have found their way in there.
Yeah.
But one thing I liked about what Akshay in his
Hmm.
talk was talking about is that he said this might be a moment where the mathematics community makes a shift that we probably should have made like 20, 30, 40 years ago.
Yeah, interesting.
Because, you know,
Hmm. Hmm.
one big question I've had is that like there's this notion that so much of this advanced mathematics is just incomprehensible. Like you can't explain it even to other mathematicians a lot of the time. And having plumbed, I haven't seen everything, but having seen a lot of those more advanced things, I don't think
Hmm.
it's undoable to make it understandable. I really don't.
Hmm.
I think a lot more of it can be made understandable to a larger audience, and
Hmm.
I think some sources have done a decent job with that. Like Quanta's been doing a good job, but sometimes
Yeah.
like
Yeah.
I read a Quanta article about a thing called sheaves, and sheaves are one of these
Hmm.
pretty abstract things, and like you usually first see in algebraic geometry, maybe differential geometry. And
Right.
they gave an explanation which I think was like good, and it's actually the common like intuition based explanation that you would get even in a math class
Uh-huh.
that I think is kind of not that useful.
Oh.
Because what they did is a lot of mathematicians they gave like a literal explanation of like here's what the object is like. And where its name comes from is because it's kind of like a sheaf of stalks of like a hay or whatever.
Yeah,
And
I've
they gave
seen
that
some sort of
explanation.
hay like wire diagrams or something.
Yeah,
Yeah.
yeah,
Yeah.
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 And it's like, yeah, that's a decent way of thinking about it. And there's a lot of constructions where we even think about that. That's how we visualize it. But that's a
Hmm.
different explanation than the question of why do we use sheaves? Like, why
Yeah.
do we
Yeah.
use these at all, period? And the
Right.
reason that is because a lot of times just sort of functions aren't enough, or the function's domain might be like locally simple, like it might locally look like, say, even a map just between two vector spaces, but you want to glue things together. Like usually things continually vary. And when you do this, like when you ask what is the actual natural thing I'm trying to look for, if I have a function, what should its domain look like? You'll get a sheaf. And that's really where it comes from.
Hmm.
Is that like really we
Oh,
use sheaves
interesting.
because we want to glue together domains.
Mm.
Um, and so I think much more of this can be made understandable. And like
Hmm.
that's something that I hope to do. I haven't done much with this YouTube channel, and maybe I'll do different things when I have a little more time. But
Yeah, with the
it's
infinite free
interesting.
time that we all have. I'm glad
Mhm.
that you bring up Quanta as the example for this because
Mhm.
I've just been so blown away like over the last so many
Mhm.
years. Like I don't know when they started, but I just
They're
started
doing a great job.
noticing.
They are,
Yeah,
yeah.
yeah, like their articles started popping up on Hacker News, and I was like starting to recognize like, oh yeah, this Quanta like is just way
Mhm.
better than the like popular science websites that I remember like
Yeah.
from when I was in college. Um,
Yeah, there's
yeah.
we often talk in memes. I actually have a friend who's
Hmm.
in logic, and he's he's gone around talking to three different science YouTubers right now where they're asking him questions about like Gödel's incompleteness and
Yeah. Right.
independence of the continuum hypothesis. And those are two things where kind of the popular notions of them definitely, at least in my opinion and in his opinion, don't really match what the intuition should be. Like oftentimes
Mm.
when I'm trying to teach or explain something to someone, I care more about being, say, more what I would call morally right than like
Hmm. Hmm.
precisely correct. Like I want them to
Hmm.
come out of it with the right idea of what's going on, and the
Same.
details they can get from any textbook or whatever. And
Yeah.
the details still matter, like the technical details, but I
Yeah.
think if you're giving a lecture, you're a little bit wasting your time if you only talk about, say, the details of the proof and make sure that all the I's are dotted and T's are crossed, because you can just get that from any direct source. I think in a lecture, that's where you should be getting the intuitive idea that like if, because I also think when people have the more, what I call the morally correct idea in their head, when they
Hmm.
understand it, they can reproduce those proofs. And when details are
Yeah.
off, their intuition will lead them down the right path.
Hmm.
And like I think the intuition and like idea that most people get from girdles and completeness is not quite right. Like I think some
Yeah.
people think it's like, oh, truth doesn't exist in mathematics, and that's not really
Yeah.
what it's
Yeah.
more that
Yeah.
saying like if you make a system, it can't prove itself true or its own
Hmm.
consistency, which is about the
Hmm.
same as like when you're speaking, it's like if you say this statement is false, like that's not
Yeah.
irresolvable, but you can still communicate just fine with other people. So,
Right, but on that, like, I know that this is just an example that you're giving, but
mhm.
with Gödel's incompleteness theorems, what I find fascinating is
Mm,
that there are like not those pathological examples of like self-describing
mm.
statements, but there are real, meaningful, interesting questions like the continuum hypothesis, right?
Yes,
Like
yeah.
that is to me just the single counterexample that's like, well,
Mm.
it's not only these like you know who Barb's a barber or whatever like type of
Yeah, yeah, yeah.
paradoxes.
That's an
Um,
entirely different thing going on there, and that was something that I also didn't understand until I read a thing about set theory and category theory, which
mhm.
actually helped me probably understand most of logic to this day. It was kind of like one of those things where a logician writes something for the mathematicians who aren't logicians, and it was super useful.
Yeah,
But
yeah,
basically,
yeah. Can I interrupt real quick just to
yeah, yeah,
finish
go
that
ahead.
thought? Is
Go
last
ahead.
thing I was gonna say is like my I had that like pop science understanding
Mm,
the first time I learned Gödel's incompleteness theorem.
mm,
I was just like, this is crazy. Like I'm a philosophy minor, and like this means so
mm,
many philosophy types of ideas. But then after like a little bit of time and like actually taking a math logic course, my takeaway was like, oh no, what it really proves is that this specific form of logic is incomplete, like first
mm,
order logic, as I understand it. Like,
mm.
um, that's the level of my foundations kind of understanding. I know that there's something called second order logic and like other, kind of
Yeah,
work
second
that's
order
going on.
logic
And yeah, and it
it
doesn't
is
apply there,
interesting.
right? Like that's my understanding, or maybe it's an
Well,
open
it's like
question. Yeah.
the real thing is if I have a logical system, it's not powerful enough to show the consistency of itself. But for example, there's
Hmm.
a smaller system that's just called piano arithmetic, which is where
Hmm.
you have these statements like for all n there exists, I don't know, p that divides n, and that could be one,
Yeah.
you know. That's
Right.
a statement in piano arithmetic. And ZFC is strong enough to prove that that's consistent because it
Okay.
can make a
Right.
model of it.
Right.
You can make the natural numbers and you can show that everything works out. And so, for example, you can make bigger assumptions and prove the consistency of ZFC. Like
Hmm.
there are these things called large cardinal axioms. But basically, what's saying, which is basically, I would say, a useful technical result is whatever assumptions you make, that set of assumptions can't prove that itself is consistent. And so
Hmm.
you can never wish for that. But there could be something
Right.
stronger. So it's like I'm trying to do number theory and then I can't show that it's consistent within number theory. So I come up with ZFC, and with ZFC I can show that number theory is consistent. But then the question is like, how do I show that that's consistent? It's like, well, I can come up with large cardinal axioms and that can show that that's consistent. But this
Hmm.
chain never ends is the problem.
Yeah. Yeah. Hmm.
That's really kind of what Gödel tells you, and that's interesting.
Hmm.
But the continuum hypothesis stuff is a totally different thing where basically the way I would describe it is that like the rules of ZFC don't tell you everything about all the sets. Like an example I would give is that like I had a conversation with a friend just the other day explaining the continuum hypothesis, and
Hmm.
I could do that now, but if you want to talk about something else, that's fine too.
I'm
Um,
here for whatever you want to talk about. This is great.
sure. Yeah.
I think
So
we like broadly touched or like covered the like science versus art kind of
yeah,
thing. It's
yeah,
like
yeah,
the real answer I've always thought is both. Like it is
yeah, yeah,
both.
yeah,
Yeah, so
yeah.
cool.
And but for the continuum hypothesis, the way I would put it is like imagine you were an actor and somebody handed you a script. Maybe it's a scene
Hmm.
in a mall. and they say, okay, so you're standing by the subway and you're having an argument with someone and like something happens and then you exit left, whatever. It gives you
Hmm.
these details. It gives you dialogue. You say this, maybe it's a 2 minute scene, right? And so
Hmm.
you read this script, you know a bunch about the scene. And then somebody asks you, okay, how many extras are in the scene? And it's like,
Uh-huh.
I don't know. And it's like, how many is like, what did the extra in the background order? And you go, oh, I don't know. Um, and basically what's saying here is that like the analogy here is ZFC is kind of like the script. It tells you enough, but it doesn't tell you everything. There's just stuff that's like kind of left out. And the
Hmm.
reason we also don't really want it to tell you everything because if you add too many assumptions, you might accidentally create a contradiction, which would be
Yeah.
bad.
Right.
And so things like the continuum hypothesis is basically, okay, we found a question that is like the question, how many extras are in the scene? You just
Hmm.
don't know. And like another
Yeah.
example that I give it is that like ZFC is
Hmm.
kind of like an API, but
Yeah.
any specific theoretic universe that you're working on, something does happen in the back end. You might not know what's going on in the back
Yeah.
end. And so the
Hmm.
continuum hypothesis may be true or may not be true in whatever mathematics you're doing. But
Hmm.
for the most part, for most of the mathematics we do, we don't need to know if it's true or not. Like,
Yes, absolutely.
yeah,
And then now, I mean, you said that
mhm,
you prefer math as an art, but
yeah,
now in a sense you're talking about the what's the word, veracity or whatever of math,
hmm,
and like
yeah,
um to me that's like math as a science. Like math as an
mhm,
art would be like, can we answer this question? Like it,
mm,
I think in some sense, like as long as, and I know that we're like treading into waters where like I just
hmm,
don't know anything at all, and I'm a
yeah,
hobbyist talking, but like in some sense, like if our definition of real numbers via
mm,
Cauchy sequences or whatever is a meaningful statement, then like there has to be an answer, like law of excluded middle kind of thing,
I
right?
can go into
Like
that.
it should be one or
So,
the other. Yeah.
so
So.
here's the very, very short overview of what Cohen did with forcing that doesn't talk about any of the technical details.
Mhm.
Because actually, the technical details, both in like Gödel's proof, like the
Mhm.
technical details in Gödel's proof, is that he builds a computer out of like number theory statements. That's
Yeah.
what he's doing.
Which, by
Um,
the way, the number file video on this is incredible.
oh yeah,
If
I haven't
I
seen it.
think it's
Interesting.
number file. Yeah, yeah. They show like it reduces down to fundamental theorem of arithmetic and like
Yeah,
representing math symbols as
yeah.
primes, and every math statement is a multiplication of primes,
Mm,
and then you get your like diagonalization argument or something.
I
That's like
see.
my like rapid fire
Yeah.
understanding. I do not understand Gödel's incompleteness theorem properly, and I'd love to learn it
Well,
properly here someday. But
I'm
yeah,
thinking of doing like a long video on basically explaining all the diagonalization proofs, and
cool.
there's some other YouTube videos that do a similar thing, but the other thing I want to explain is there's in a
Mm.
lot of settings you can actually de-diagonalize, like you can fix the
Hmm.
paradox.
Oh,
And I haven't
interesting.
seen anybody go over that, and so I'm
Hmm.
thinking of that, maybe making a long video, literally going over like Cantor's all the way through Gödel's through. There's a proof that you can't use diagonalization to prove p is not equal to np. Talk about that, and
Oh,
talk about how
oh
to
yeah,
make
yeah. Hmm.
talk about how to make settings where stuff like Gödel's incompleteness doesn't work. But
Hmm.
that would be a long time in the future. I'm busy with various other things now.
Right.
But yeah, going back to like what's going on with the continuum hypothesis. Here's what Cohen's proof kind of does. It sort of says like if we go back to the analogy where like the script is ZFC and a scene is like an instantiation, it's like we've made our universe of mathematics. We call them set theoretic universes or universes for short.
Hmm.
And what forcing does is says, okay, suppose we have a universe. Suppose a universe exists, which is actually the same as the statement of the consistency of ZFC. So you're already assuming a little more than ZFC just by saying a universe exists. Suppose we have a scene, like we've filmed a scene where you're outside the subway and there are some extras. You know, somebody orders something in the background. What forcing did is like, okay, if there are extras, we can also make a scene where there are no extras in the background.
Hmm.
Like we can just remove the extras. And that's something you can if you so this is where all the technical details happen of what
Yeah.
forcing is like
Hmm.
how do we remove the extras? And then
Yeah.
also with forcing, they say it's like, well, if we have a scene where you're arguing in front of a subway, we can also add in a bunch of people. We can have exactly 3 extras or exactly 5 extras. We could have like a group of
Fascinating.
school children
Yeah.
walk in the back. And so this
Uh-huh.
is actually what forcing does. What they say is like, if we have a universe, we can cook up a consistent way of doing set theory where there's no infinity between the natural numbers and the real numbers.
Hmm.
And we can cook up where there's exactly one infinity. We can cook up one where there's exactly seven or where there's exactly countably many infinities in between them. We can
Yeah.
do all of those things. And so when it says like there must be an answer, it's kind of the same as like saying, well, there must be an answer of how many extras are in that scene. It's like, well, there can be a lot
Mm-hmm.
of, you can film that scene many different ways. You
Huh.
can make your set theoretic universe a lot different ways. Does that
Huh.
sort of make sense?
Yeah, that's really, really interesting. That's
Yeah,
I'm
yeah.
gonna have to like digest that for a little bit because it intuitively just feels wrong to me somehow. It's
Yeah,
like
yeah.
there
So
should
what you're
be,
coming
but
up
like,
against
yeah, I think.
is that and this is something because my friend who's a logic PhD is literally talking to maybe I should it's 3 big YouTubers who all like science YouTubers 1 million plus subscribers. And he's literally advising all 3 of them on like set theory and logic stuff.
Oh
And
wow.
I texted him and I said, you should try to make it clear the difference between ZFC and individual set theoretic universes. Because if
Hmm.
people can
Yeah, yeah, yeah.
understand that
Mm-hmm.
difference, if they can understand the difference between a script and different ways to film a scene, then they will understand why all of these things are
Mm-hmm.
possible and it will be less paradoxical. Like that's the thing that I
Right.
think most people
Okay.
are missing. That's the thing I think
Yes.
most explainers are missing. And if you like get that that basically there are multiple universes, sort of like how there are multiple
Yeah.
groups. Like you have the
Yeah. Yeah.
axiom of a group, but there are tons of different types of groups. You have the
Mm-hmm.
axioms of ZSE, there are tons of different set theoretic universes. And so that's what
Yeah.
goes on with forcing.
But is this different than saying that there's alternatives to ZFC? Like when you say that
Yeah.
there's many set theoretic universes, or
Hmm.
okay, is it different than saying that there's alternatives, or
Well,
like,
so yeah, it depends. Yeah, set theoretic universe. A lot of people take ZF set theoretic universes. You can make a universe where choice doesn't hold, for example.
uh-huh, right?
Um, and so basically, it's kind of like we have lots of types of mathematical objects. We can have groups, we can have vector spaces, we can have rings, fields, whatever. And all of these things are a list of axioms, and
Yeah,
each individual field is like the difference between the definition of a field and a specific field, like the real numbers or the complex numbers.
of course. Okay,
Like
yeah, yeah,
uh
right.
like and for example, in the real numbers, x squared equals -1 has no solutions.
Mm-hmm.
And that's just a field
Right.
theoretic statement. But in the complex numbers, x squared equals -1 has 2 solutions. And that's kind of like
Right.
how I can have 2 different set theoretic universes, like the statement, there's an
Yes.
infinity between natural numbers and real numbers, and then
Uh-huh.
can be true and false in 2 different set theoretic universes. Um,
Yeah. So I mean, that's where I'm having
mm,
some challenge because it's like there in my like intuition there are mathematical statements
mm,
that are true, you know, to aliens, like to anything that
hmm
can like distinguish, like counting,
yeah,
like separating this versus that. You at some point you want to line things up in a grid, and then you have
hmm
multiplication, and then you find out that there are these prime numbers, and you can only
hmm
like list them in one long row. Um, and so to me, there's some kind of idea that prime numbers exist in nature. Like,
mm,
and I don't know. Yeah, like I would love to understand more of the, because
mm.
like there must be an argument here. Um,
Yeah, yeah. I think
but
what so
yeah,
I think a lot of people feel and mathematicians feel the same way you do. And what you're really getting at is like statements in piano arithmetic. Statements you can make with
exactly.
positive
Yeah.
integers.
Yeah, and so
Um,
then what I'm like super curious about is like where is the line? Because like certainly there
mm,
is math that we're inventing that I think is
hmm
only meaningful in ZFC or in like one
hmm
fixed axiom system.
mm,
And so yeah, there's no I don't have any challenge or qualms about like ZFC is, or a continuum hypothesis is undecidable in ZFC. It's true in another axiom system. It might be false in another one. Um, you know, I, somehow I believe that there might be consistent alternatives to ZFC that even contain piano arithmetic,
Mm.
where continuum hypothesis is true in one but not the other.
Mhm.
But I have a hard time like imagining like a meaningful quote unquote axiom system that doesn't include piano arithmetic, that doesn't include
Mm.
prime numbers, because in some sense that's in nature. And in
Yeah, yeah.
from that perspective, it's like, can we categorize the math that like is in nature versus not? Like
Yeah,
things like that.
the way I would think of it, and this is how I do think of it, is really anything finite computational, which is the same
Mm-hmm.
as piano arithmetic. That's the work of Gödel's, is building computers in those statements. And so like anything that's like a question like a Turing machine,
Mm-hmm.
will it halt in exactly n steps? You know,
Mm-hmm.
all of those statements I would say are kind of like the natural statements.
Yeah.
And you could argue that and some people do, that everything else is invented.
Yeah.
And I think that's fair to argue. I think a lot of them make sense in their inventions. Like kind of some people have qualms with real numbers because they
Mm-hmm.
have infinitely many digits. But if you think of them as just like filling in these limits, it's
Mm-hmm.
like a lot of things, say you were stuck to only rational numbers, a lot of things would have an answer that's really like square root of 2 or like cube root of 3 or something like that. And then if you want to
Mm-hmm.
like that's the maximum point. And then to say maximum, you would say, well, you get these sequences that go in this direction and it always gets bigger, but there is no maximum. It's like, well, it looks like all those sequences are going to one place, so it feels like we should just give that a name and call it square root of 2 or cube root of 3
Right.
or whatever. And so,
Right. Yeah, this is
yeah,
kind of like the computable calculus or something like that. I think
yeah,
I've heard about that, like some sort of
yeah.
like. Okay. Anyways, yeah.
But it's
Okay.
but I think these are interesting questions. Like one bet that I have is the aliens, their foundations are not ZFC.
Right.
Like and of course, that can be like, you can take that in a very weak way, and that their foundations aren't exactly those axioms, which is be like, well, duh, like they
Mm-hmm.
might be slightly
Mm-hmm.
different. But the way I put it is that they don't have every single object in mathematics be a collection of collections of collections all the way down.
Okay.
That
Okay.
which is sort
Oh.
of like what the set theoretic paradigm is, that everything you can view it actually like a big directed graph where like you have
Mm-hmm.
a node from A to B if A is contained in B.
Okay.
Or yeah, A is a member of B, not like subset is a member of. And that's how some
Okay.
people
Right.
think of it. Like some people think of set theoretic universes as precisely directed graphs with exactly out degree one. Well, not out degree one. I would have to think about well, no, you can have containership. It would be, what is it? It's a finite, what's called, no, it's a rigid tree, which is so
Mm-hmm.
you can think of a set theoretic universe as an infinite rigid tree, which is a tree that has no automorphisms, which is kind of interesting. Like, because I do some computer science stuff, when I
Mm-hmm. Mm-hmm.
learned that, I was like, I had to think about it a little bit, but you can induct from the basis of the like empty sets and show that, oh yeah, if you draw the tree that's all the containments, that tree has zero automorphisms. You can never swap two branches and have it be the same, which is interesting. Because you don't see trees with no automorphisms much ever.
Yeah.
Um,
This is fascinating. You
yeah.
are starting
Yeah.
to lose me, but it's
Oh,
like
that's yeah.
piquing.
Sorry.
I mean, it's piquing my curiosity in like such a
Yeah.
great way right now. I guess,
Yeah.
like, I don't mean to say like don't go that direction, but like, what's like the first, like, do you have a recommendation for a textbook or a resource to take the first steps towards understanding this field of math that you're referring to right now?
Like
Like,
kind of various stuff in logic.
I suppose so.
Yeah.
Yeah. Like.
Yeah, that's a good question because I'm not a logician. Like
Mhm.
everything I've learned has been kind of tangential. Because
Uh-huh.
like I learned about a lot of these large cardinal axioms because I was confused about what you could do with the category of all sets.
Hmm. Hmm.
Because like you grow up and they say you can't have any set of all sets, and that makes sense. But then you get to category theory and you can have a category of all sets, and it's like, wait, what are you talking about? And
Right,
then
right,
you can have the category of all categories, and it's like, okay, really, what are you talking about?
right.
And actually, if you're curious, like talking about second order set theory, Grothendieck universes, which is a different thing, is the same as a second order set theory. They're the same thing. They're equivalent.
Interesting. Okay.
And so some people call them like, I don't know. I'm not a logician. I'll get the name wrong, but second order set theory is the same as how you do like category of all categories, and some
Yeah.
people think it's kind of fake, and I understand why. But yeah, so I'm not a logician, but the way I learned it is the first thing where I really started learning this stuff was this one PDF by Mike Schulman, which might be useful to you. But it
Cool.
was Mike Schulman
You know what? You don't
set
have to. Well, I mean, you can
category.
type it. Please do. But
Yeah.
just in case, just in case you're taking notes, I've got the robot doing our work for us right now. We're gonna
Oh,
get like
really?
a fantastic AI summary out of this Zoom call. Um,
Interesting. Yeah,
yeah,
I'd be
it's
interested to see it.
phenomenal. Yeah,
Yeah, yeah.
I'm
So
really interested in it for this
yeah,
combo.
so
But
Mike Schulman set theory
mhm,
for category theory. That but
cool.
that's for someone who's trying to understand the set theory stuff. And the example it gave that I think is like my actor scene analogy is that, say somebody gives you the axioms of group, can you tell me whether it's commutative or not? And the answer is no,
Interesting.
because there's non-commutative groups and there are commutative groups. So I literally can't answer that question. But I've given you all these rules. It feels like I should be able to answer this question, but the rules are underspecified. It doesn't tell you everything.
Oh. Hmm.
And so that's what's going on. But the other stuff of like learning about this rigid tree stuff, Richard Borchers
Yeah.
has a very good
Cool.
series on set theory.
Uh huh.
Richard Borchers
Hmm.
is great. And
Highly
then
recommended to everybody.
yeah, yeah,
I mean,
Borchers is great.
yeah,
I think he's the best kind of YouTuber for kind of like technical stuff
yeah,
in
yeah.
math. And
Hmm.
other than that, a lot of these things I've just seen from various talks.
Uh
Because,
huh.
one of the reasons I'm so confident in this bet that the aliens don't use ZFC is that I'm not convinced we're going to use ZFC.
Oh, cool.
Because
Hmm.
I think within my lifetime is a good chance that the foundations change.
Wow.
And so, like, if we were the aliens and we land somewhere else, we're not using ZFC either.
Cool. Yeah.
Um,
Yeah.
and so yeah, but the rigid tree stuff, like, there's also, if I'll mention one other thing, you can encode finite set theory and piano arithmetic too. There's a lot of things which are equivalent. All of the like statements that you can make with Turing machines is like the same as piano arithmetic, which is the same as a finite set theory. So if you take the universe of finite sets, you can uniquely encode every single finite set as a positive integer. And the way you do it is that, say I write the number m in binary,
Hmm.
then so the set corresponding to m is
Yeah.
exactly, you take its kth digit, and if that's a 1, it contains the set corresponding to k. And so if I take the number
Right.
m, so say I take the number 4, then that set is the set that contains the number 2 because it's 1, 0, 0. And then I
Okay.
take the number 2, and that's the set that contains the set named number 1, and
Uh
1
huh.
is the set that contains the empty set. So the number 4 is exactly the set that starts with the empty set, and then 1 containment, 2 containment, 3 containments.
Yeah. I mean, isn't that's piano arithmetic, right? Like, isn't
Yeah,
that
yeah,
how
yeah.
you? Yeah. Like, that's vaguely what I remember
Yeah.
of. Yeah, how you define four. It's like the successor of zero, successor of that, and
Yeah, yeah,
a
yeah.
successor
They
is
do
like
it
just grouping or something. Yeah.
they
But
do it slightly differently. You can do it that way.
mhm,
It's a little more difficult to define some things that way. But
mhm.
generally, that scheme of like, if you take the number 5, that would be the set containing 2 and 1,
Oh.
which would be different than how you would do it
Oh,
in a
because
piano
it's
arithmetic.
binary. It's not
Yeah, yeah,
just.
yeah,
Oh,
yeah,
okay, yeah. And then
yeah.
when you said that we're talking about like finite sets,
Hmm.
like I understood that to mean like a finite collection of things, but it sounds like you're talking about the
Yeah. So
numbers, like finite numbers or something.
yeah,
Yeah.
so much. The problem and where we get infinity, I always think comes down to like when you're playing the biggest number game as a kid, and you can always say your number plus 1.
Uh-huh.
That's really kind of why we have infinity and what kind of started all these problems, you could say, is that
Right.
like there really is no biggest finite number, and but you can take
Mm-hmm.
the
Mm-hmm.
axioms of ZFC, you can remove the axiom of infinity, and you can make a universe that works for that with just all the finite sets.
Oh, okay.
And every single axiom will
Oh,
still be
cool.
true, which is
Hmm.
interesting to think about in of itself.
Yeah, because that's not obvious, or it looks like you have to go soon. So, yeah.
Yeah, I gotta go head out and talk to people about actually like stuff related to zero knowledge proof stuff on GPUs that people are trying to get
Damn,
these things implemented efficiently to verify computations.
that is freaking
Um,
cool. Yeah.
yeah.
All right. Where can people find you? Um,
Yeah, on Leo Lectures. Hopefully, yeah, I hope to put some more stuff on there at Leo Lectures on YouTube, and like maybe of a slightly different kind. I might try to do a better produced kind of video on all of these diagonalization stuff. I have a friend coming next weekend. Maybe we'll do some of it then. Um,
cool.
but yeah, it's fun to chat, and I think these are all good questions. And I think math could use more stuff like what you're doing, like where you're just talking about and thinking about these bigger concepts and trying to make it more understandable. Because like I've been a little bit disappointed with the pure math community because it feels like the idea of that is to look for these aesthetic stuff, but we put almost no effort into making it understandable for other people. And it
Yeah.
is doable. Like some of the story
Hmm.
people say is like, oh, it's just too complicated.
Yeah.
A lot of it is, some of it's more easier to make understandable than other things, but so much more, we can do way more than we do right now. Way, way more. And
I
so
can.
like I think
Hmm.
what you're doing is great. Also, saying it's like, yeah, you can do it as a hobby because it's an enriching thing to do. And
Absolutely.
so yeah,
Thank you.
yeah. I hope things
Yeah.
continue to go well. It's great chatting.
Yeah. It was really great to chat. Thank you so much for this chat. This was
Yeah,
fun.
yeah. See you, man.
Yeah. All right. Next time. See ya.